All right, let's jump right into this explainer. Today, we're tracking a really fascinating architectural refactoring journey based on a developer's detailed notes on Haskell programming. If you've ever dealt with the absolute headache of working with flat data structures that just refuse to scale as your app grows, you are definitely going to relate to this. We're going to see how shifting from a chaotic, flat way of parsing data to a highly structured domain model completely transforms a codebase. So how do we escape tedious list manipulation? Look, we've all been there, right? It's that universal developer pain point. You write a parser, you dump literally everything into a single flat array, and suddenly every single time you need a specific piece of information, your code is forced to iterate over the entire stream. It's tedious, it's totally error-prone, and as we'll see today, it's actually completely avoidable. To fix this, we're going to contrast two totally different architectural approaches. On one side, we have the flat token stream, which was the chaotic original starting point for this project. And on the other, we have a beautifully ordered, structured, abstract syntax tree, or AST. We're going to trace the author's transition from left to right and really unpack exactly why this transformation is such a game changer.
Okay, let's look at the flat token stream first. Basically, the initial parser just dumped every single extracted element into a flat list, defined in Haskell simply as a list of tokens. You can think of it kind of like a massive junk drawer in your kitchen. You've got metadata, headers, standard text paragraphs, all just jumbled together in one undifferentiated array. I mean, sure, it technically works, but an array like this fundamentally lacks structural context.
And here is the big problem with that. Tedious extraction. Because everything is literally just shoved into that mixed flat array, your downstream processes, like a data converter for instance, have to do all the heavy lifting. If your converter needs to find the author's name or maybe a keyword index, it has to scan the entire list from the top, checking every single item just to see if it happens to be metadata. It creates so much unnecessary complexity and leads to incredibly brittle code.
Enter the hero of our story, the Structured Abstract Syntax Tree, or AST. To fix their parser, the author replaced that messy flat list with a strongly typed structure. The beauty of an AST is that it clearly separates the overarching document structure from the actual content blocks. So instead of that single mixed junk drawer, every piece of data now has a specific, perfectly labeled filing cabinet where it belongs. To pull this off, the author built this structured domain model using three brand new foundational data types. We have metadata, which handles the overarching details of the book, document, representing the entire parsed file, and finally, block, which manages the granular pieces of content. Let's zoom in on each of these individually to see how they actually build a more robust architecture. First up, we have metadata. This cleanly isolates all those book-level details extracted from the YAML-like header. It holds the title and the author as text, and it holds the index as a list of text keywords. By giving metadata its own dedicated type like this, we completely eliminate the risk of the system accidentally treating a book title like it's just another random paragraph in the document. Next is the document type. You can think of this one as the master container for the whole file. It elegantly holds an optional metadata field, which is represented in Haskell by maybe metadata, alongside a document body composed entirely of our third type, blocks. So the metadata isn't hiding inside the body anymore. It sits right at the very top level of the document, completely separated from the content itself. And finally, we have the block type. This handles the actual on-the-page content of the file. It specifically differentiates between a header, capturing the header type, the level, and the text, and a standard text paragraph. Because the overarching metadata has already been stripped out and stored safely in the document type, the block type literally only ever has to worry about structural content. So with this beautiful new filing cabinet structure securely in place, the parser code naturally needed to evolve to match. The author mapped out three logical steps. First, update the metadata parser to explicitly return the new metadata type. Second, update the header and paragraph parsers to return the block type. And third, update the main document parser to return that master document type. What's really cool here is seeing how the generic ptoken parser got completely swapped out for a highly specific pblock parser. In the old codebase, ptoken was just a catch-all. It chose between a header and a paragraph and spit out a generic token. The new pblock parser makes the exact same choice, but returns our specific block type. This tiny swap makes the code's intent instantly clearer to anyone reading it.
And right here in the P document parser, oh man, this is where we see the real architectural payoff. Look at the old approach. The code had to clumsily convert optional metadata into a list and then concatenate it with the body list using that append operator. It was literally shoving everything back into one flat array. But now, the code simply instantiates a clean document object, passing it the metadata and the body as distinct separated arguments, much cleaner. The author hits the nail on the head with this quote: "By switching to a structured approach, we avoid the hassle of list manipulation." And let's be real, if you write code, you know that avoiding list manipulation is just very polite developer speak for finally ending the absolute torture of writing endless loops to search through massive arrays. It is a massive relief for maintainability. So what's the actual payoff? Well, it hits during the Pandoc conversion phase. Because we have our new document type, we can extract the metadata directly from the document structure. No list scanning required whatsoever. We don't have to filter through hundreds of paragraphs hoping to stumble upon the book's title. It's just sitting right there in the document's metadata field, totally ready to go. You can physically see that difference right here in the Pandoc conversion functions. The old tokens to Pandoc method was basically flying blind. It just mapped a function over the flat list of tokens and sort of hoped for the best. The new function, doc to Pandoc, takes the document type and handles things with absolute intention. It conditionally adds the metadata if it's there, and then it separately folds over the specific content blocks. It's incredibly precise. And as the author notes regarding this exact step, metadata processing is now cleanly separated from content transformation. This quote brilliantly illustrates the core architectural victory of the whole refactor. It's a complete and total separation of concerns. The parsing logic is cleaner, the data structures are totally explicit, and the downstream functions can finally do their jobs without any dangerous guesswork.
Okay, let's do a quick recap of the refactoring benefits here. First, this AST approach gives us a highly robust architecture that saves precious developer time by resolving all that tedious list processing. Second, it dramatically reduces code complexity by completely eliminating the need for list scanning. And crucially, it fixes the underlying performance drag of iterating over those massive flat token lists. It's literally a win on every single front.
But, the journey of refactoring is literally never finished, is it? The author actually points out a next evolution. While this internal AST is a huge leap forward, there is a potentially even more elegant solution on the horizon: hooking a custom parser directly into Pandoc's engine by creating a custom Pandoc reader rather than managing an internal AST document at all. Which leaves us with this awesome, kind of provocative question: will discarding this newly built internal AST entirely for a custom Pandoc reader prove to be the ultimate architectural triumph? I mean, sometimes the absolute best code is the code you can delete entirely because you've leaned into powerful external engines. It's a fantastic thought experiment. Thanks so much for hanging out with me on this explainer, and I really hope this dive into structured data inspires your very next refactor.